So for the pair interactions, the simple, that's the total energy at a time t. It's just given by pairwise interaction of atom I sitting at position xi, so should be a vector. And we have to sum over all I and j. I should not be equal to j. And since if you do it this way, we count every bond twice, we put the factor 1/2 in front of it. Since our system,
If you take I not equal to j, you don't need the factor of half, right? If I have 3 items, for example, 1 and 2, 1 and 2.
No, I mean this is...
2 and 1 is not calculated because I is not equal to.
No.
You're not taking I greater than.
I could avoid the factor 1/2 if I put I greater than j. Yeah.
You are only
I am just excluding self-interaction. Yeah, I mean the atoms, they are not interacting with themselves. I could put it also
No, that's okay.
like this. That's the same. I emphasize this point because I was confused this morning when I was going through some calculations of the Lennard-Jones potential, and I think I took something from a literature source. Maybe I made a mistake, maybe they made a mistake by this factor of 2, so there's a factor of 2 missing at least, so we can look to it. So since the system is translationally invariant, does not depend on where I put the origin. This can depend only on the distance. So I keep this factor of 1/2 here. And also we assume that it's rotationally invariant, so it can depend only on the absolute value of this distance here. Yeah, and as we already heard in one of the lectures before, or as you probably know from mechanics, the forces then are obtained as differential derivative of this potential energy at the time t. And the simplest model is that going back to Lennard-Jones. This name Lennard-Jones is not 2 persons, but it's 1 person who had this name Lennard-Jones. Yeah, so I think we have a couple of such cases where often one thinks. I think Hume Rosary is also 1 person. It's not 2 persons who invented these rules, which you probably know. So what is it? That's this person here. He proposed this simple model in the 30s of last century. It describes here the interaction of 2 atoms. If they approach each other, if they get too close, there is a repulsive force because the nuclei would overlap or the core electrons would overlap. There are also quantum mechanical contributions there. But if they have a certain distance, you have the attraction here due to the electronic shells. It's just a cartoon of what happens, which adjusts the equilibrium distance. So the functional dependence is given here. We saw it already. I omitted the sigma here, which scales the distance. So this is the functional dependence, power 12, power 6. And the reason is not given by any physics, why he chose these 12 and 6. And there are also other models with other powers here. It's just because computations are particularly simple with these special powers here. Yeah. So in principle, there's a further factor here, sigma, describing or scaling the distances here. And we have a minimum at this position. But there is one complication. If we apply this potential to our crystal, maybe I should switch back to my notes. The atoms, there's not only one pair of atoms, and there's not only one partner in some distance, but there are many atoms surrounding a particular atom. So perhaps write it down here again. I now write it with a sigma like this. That's the interaction between two atoms. Now let's assume that we have a lattice, for example, an FCC lattice. With one atom sitting here in the corner, and the other atoms sitting on the other corner sides and on the face centers. And of course, this atom interacts with this one, but also with this one, and so on. This is simple, but then there's also the second neighbor here, third neighbor, fourth neighbor, and so on. Yeah? And the total energy is not only given by the next neighbors, but by all neighbors. Yeah? This you should keep in mind. So the equilibrium distance which we reach in a crystal is not just the minimum of this energy, this potential. I forgot one point. I should, before I continue here, I should calculate the minimum of this Lennard-Jones potential. I think it's on the next slide, I guess. No, I don't have it here, so we briefly do it. This factor is just if you take the derivative and put it to 0, so it's, I think it's 2 power 1/6. And the depth of the potential is -4 epsilon, so if minus epsilon. So the value at x0. That's why we put this factor in 4 here. Typically what you do and what Guru already did is that we put sigma and epsilon to 1. So then the minimum is at -1. And so the value of the minimum is -1. And the position of the minimum is at 1.12. Okay, but now we can go to this summation over the lattice points. So the total energy of a crystal, or at the moment it's not particular for one lattice, but I do this. Again, we have this factor 1/2 here, number of atoms, because the interaction, of course, is the same for each atom here. And then we have to sum up over all I from 1 to infinity. Over all the neighbors of one atom. Yeah? And we can make a little table for an FCC lattice. I think the situation is not that simple for other types of lattices, so it's where we stay. And luckily, many structures are FCC in metallurgy. So what are the neighbors in FCC? So I put the I here. What's the first neighbor in FCC? I guess you know on this lattice. I mean, what are the coordinates? Yeah, it's this one here, 1/2, or if we have A, this is the lattice constant. It has the coordinates 1/2. Like this. And how many of these do we have? I guess, again, hopefully you know, it's 12 neighbors. What else do we need? The distance here. It's sorry, it's of course not A but 2. Okay, and the second neighbor, just the neighboring atom here, one lattice constant away. It's this one here, so it's 1, 0, 0. So distance is 1, x2. And the multiplicity is 6. The third is already a bit more difficult. Who knows the coordinates of the third neighbor? I mean, if you want to do it systematically, I mean, one can, of course, go through the indices. right, yeah. It's 1, 1 half, 1 half. So it's 1, 1, 2, or 2, 1, 1, yeah. If you want to do it systematically, of course you can take all indices. You start with 0, 0, 0, and you put 1s and 2s and 3s and so on. But then the question, where do we find atoms? And perhaps you know that the reciprocal of FCC is BCC, and the reciprocal of BCC is FCC. And perhaps you heard about the extinction rules in FCC and BCC in diffraction. Since they are reciprocal to each other, you can take the extinction rules or the selection rules of BCC to find out which places are occupied in FCC. So this means that the sum of the indices has to be even for existing positions. So 1, 1, 3 is not an occupied position because the sum is 5. Yeah? So that's how when I do it systematically, I think I should put angle brackets here. Okay. The distance here is 1 plus 1 plus 4, square root of 6. By the way, I can write this a bit differently, more complicated. I write this as square root of 4 over 2a. Yeah? Then perhaps you already see the systematic. Here we have square root 2, 4, 6, and we go on like this. What's the multiplicity of 1, 1, 2? Anybody knows? Or how many neighbors of this type you have? There are also, I mean, you have 3 positions for the 2. You can put the 2 here, here, here. And then you can permute, you can distribute plus or minus here, 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 or here. So overall you get 24 possibilities. In principle, the maximum you have are 8 permutations of the indices here. So the maximum and 3 plus or minus signs. And maximum you can have 48 neighbors. But since 2 here are equal, it makes no sense to exchange these 2. So if you want to do it systematically. 4th neighbor, I stop here. It's 2, 0, 0. So the x4 is I'm wrong here in my notes. What did I do here? No, the 4th neighbor, is 2, 2, 0. That's why I did not sketch it here in the graph, because it would overlap with the other one. Yeah, so that's. And I was a bit confused because I lost the systematics here. Now we have this square root of 8 over 2, and this is the same as the first one. So it's a multiplicity of 12 here. Okay, so far it's simple. And now we can scale these distances here to the distance of the first neighbor. So if we put xi over x1, I call this k. This is 1. This is square root of 2. So like this. In this way we can now express our total energy, which we have here. First of all, we have to take all the multiplicities, and then we have these multiples of the first neighbor distance. So what we get, or I think I named it E total. To an epsilon, and now first of all we have the multiplicities here in this for the different distances where we do the summation, and then we have these factors, and we can pull out from the summation the contribution from this first neighbor here. So this becomes sigma over x1 power 12 times the sum from 1 to infinity, this zi ki power minus 12 plus sigma over x1 power 6 principle, of course, one can do the same for the BCC lattice. And you see now that these are just numbers characteristic for a particular lattice type. Yeah? That's what I did here, and you, of course, would have to continue this series here. So you can calculate these values, and then you get a function which resembles, sorry, that's a minus sign, which resembles the Lennard-Jones potential, but which is not the same, yeah? So this total energy then become, or perhaps I should first give the values here. In literature, this value is called A12, because it's for these 12 powers, and A6. And these A12 for FCC sums up to 12.13, further digits. For BCC, doing a similar calculation, it's 911. And the A6 is 14 something. And this is, and you can sum up these first 4 terms which I gave here to check, and I think they pretty well already come out to this value here. But in principle, you have, of course, you have to do the summation up to infinity. Yes? No, what?
Can you explain these terms that you have written? Summation I to infinity.
I'm not sure whether I understood your question, but I will try to explain again. So we have an atom here, which has 12 neighbors on the first neighboring shell, yeah? Which are this 1 over square root of 2 or square root of 2 half away from the central atom. So this gives the first contribution. Yeah? The second contribution is from the second neighbor. So we have 6 neighbors which have a distance of a or 1, yeah? And so on. So this is what we did here. And then we can scale. Now we can scale these factors, sigma over x by sigma over x1 power of 12 times x1 over x power 12. Yeah? Yeah? So, and these are these ki factors. Yeah? So, and then that's how I obtain this formula, this expression. And this is just a value which is characteristic for a particular type of lattice, yeah? Which does not depend on the lattice spacing. This one, of course, the distance of the neighbors, of the first neighbor, depends on the lattice constant. If I double the lattice constant, I double this one here. Yeah. Yeah, Zi.
First, second, third.
Right. This is in this table here.
Mark that 12, 6, 24, 12.
That's here. I think I have it on.
The entire crystal you have to sum, right?
Perhaps I should show the slide here. Yeah? Here, this is, which one is the green curve is a Lennard-Jones potential. Yeah? And I mark the positions of the first neighbor, second neighbor, third neighbor, and so on here, these red lines. Okay? And you see the first neighbor is already closer as this minimum of the potential would give, yeah? I think this is the right one, yeah, it's the right one. The second neighbor is outside of the minimum, but they all contribute to the total energy. So the lattice constant which adjusts is a kind of compromise between all these contributions from the different neighbors. It's the index of the neighbors.
Then my interaction is 0.
Yeah, it's the index of the neighbors. So I sum this index I. Perhaps I confused this a bit. The first I in one of the equations was just the index of the atoms, and now it's the index of the neighbor shells. Yeah? First neighbor, second neighbor, third neighbor, just the summation index.
Yeah, it's a pair, and for every shell there is a set of pairs, and they all contribute equally, so you can just multiply by the number of neighbors. So you don't have to do. That is why Zi comes. Otherwise, what would you have done? You would have taken one, and with the first neighbors, you would have had equal contribution by 12 of them, plus another 8 of them, 6 of them, another 24 of them. So we have just separated that out and said for each neighbor shell you can write one energy. That is also scaled with the first nearest neighbor. That is how you turned it into a sum which is consisting only of the geometric factors, the distance and the number of nearest neighbors, and sigma by x1 remains, and that looks like Lennard-Jones. So that is why the other one, total energy, also looks like Lennard-Jones.
So this total energy now of the crystal using this Lennard-Jones potential becomes, that's what we had before, and now it's just replacing these sums here by the names I gave, A12, A6. So it's A12 sigma over x1 power 12 minus A6 sigma over x1 power 6. Yeah? You see, as Guru said, this function looks similar as the Lennard-Jones function, but it's not 100% the same. I mean, here we have a factor 12 roughly, and here a factor 14. So they're slightly different. And that's what is shown here in the graph. So here's again the table a bit in a nicer form as I wrote it, but it's the same as before, and the vectors of these neighbors here. So, and you can try the same with a BCC lattice just to get a feeling for it. and try to figure out these numbers which I already gave also. And this graph I already showed. I always have to check. The green one is the Lennard-Jones function here with a minimum at 1.12. And the pink one here is the total energy. We can calculate in a moment here the position of this minimum and as well as the depth of the minimum. This is here the pink curve has an axis on the left side. The green curve has its axis on the right side here. I put them on different scales because the minimum here is much deeper than the minimum of the green curve here. So it's just this epsilon here. So if you put epsilon to 1 is -1 here, while this one here goes to -8 or 9. And the important thing is, and that's always the case, that the neighboring atoms are not sitting in the potential minimum. Yeah? They are slightly out of the minimum, because you have the other neighbors which pull on the atoms as well. So, and it's kind of compromise. Because this one is here, the 0 is here for the pink graph, and the 0 for the green graph is here.
So like why is that difference coming in both the graph? This gap
Oh.
in the well depth, that is that.
Think of it this way, Lennard-Jones is fair potential, right?
Yes.
If you are just taking two atoms, you will find some distance over which they will come closer and stop. You can think of it like a molecule.
Yeah.
But you are making a lattice. Now you are putting at
It's-
some distance. Yep.
I think there are two answers, yeah? So give
So-
the first one.
So you are putting one more set of atoms at some other distance. They have an energy.
Okay.
Now it will try to adjust for this, right? So a solid forms, now you have to, that is what it is shown, Lennard-Jones at every distance. So that is R1 is the first nearest neighbor distance. R2 is the second nearest neighbor distance, and so on. So all of their energies have to be added because it's a fair potential. And then you have to take a minimum of that energy. That will actually tell you where the lattice minimum is. Right? So that is the calculation that was done, that so summation Zi Ki is that. Yeah.
I'm not sure whether I got your question right, but there's also other point which is important. The depth of this curve here is, as I said, is -8 or so, and here it's -1. And the reason, of course, is because I have so many atoms interacting here with a atom of interest. Yeah? So they all contribute a small amount of energy. I mean, if I take only first neighbors, in principle I would have 12, but I have only 6 because I have this factor of 1/2, and then I have the contribution of all the others, which do not give so much, but you see it here. Yeah? I mean, this is a contribution. Oh, it's not so different. But this was the second thing I wanted to do here. I mean, to calculate the position and the value of this minimum. I come to this at the end. I mean, how do we give values relevant for a particular element? Yeah? I mean, basically, it means scaling the distances and scaling the depths. Yeah? Epsilon scales the depths, and this sigma scales the distances. So if gold has a lattice constant of roughly 4, I have to put in values for sigma so that the lattice constant comes out as 4. If I have copper with a lattice constant of 3.6 something, I have to use a somewhat smaller sigma. Yeah? And
In
same.
other words, you can see A1 to A6 are structure dependent. For all FCC that is given, number of nearest neighbors is not going to change. What will change is how far apart these atoms are and what is their bond strength,
Yeah.
which is given by sigma and epsilon. So sigma and epsilon are the parameters which will tell for what system you are using. If it is aluminum, it will some number, gold some other number, xenon some other number, and so on.
I mean, that's a good side. The bad side, of course, is that the flexibility is very limited. So apart from these two values, cohesive energy and lattice constant, the rest must come out by itself, and often it comes out wrong. And the nice thing, to put it positive, is that you can control precisely. If you vary the sigma, you vary the lattice constant, nothing else. Yeah? While for these EAM potentials, if you vary one of the many parameters, like I'll come to this in the next chapter, you never know how they influence certain quantities. So it's a quite complicated thing to really do systematic studies, for example. Yeah? I showed you this curve here, the Lennard-Jones potential curve, which has minimum at -1, and this is minimum distance at 1.12 sigma. So I rewrite it here. And now we can check the minimum of our total energy. Now I have to write it as an E of x1, because this is the next neighbor distance which we put here. I think the function is still up here. So we have to take the derivative with respect to x1. And put it to 0. If we do that, we have 2n epsilon. Yeah. 12 A12 sigma power 12 stays, and here the x1 becomes the power 13 minus 6 A6 sigma power 6 x1 power 7, sorry. And now we can throw out many of these terms. Maybe I should do it because I did it just this morning, and maybe I made a mistake. No, but I think the result was correct. So this one is not interesting, the 2n epsilon. We can take out a factor of 6. We can take out a factor of sigma power 6 x1 power 7. So I put it all here to make it clear. 6 sigma power 6 x1 power 7, and we keep 2 A12 sigma power 6 x1 power 6 minus A6. And this then finally gives our x1. So that's the nearest neighbor distance, as I still write it a bit more complicated as necessary. A6, 12 over 6, A12 over A6 all this power 1/6 times sigma. And if I put in the numbers from above, and 12 over 6 gives 2, we end up with a 1.09 sigma for this minimum. And this is what we can see here. So this is now this minimum, which is slightly to the left of this minimum. Yeah? And also we can compute the depth of this minimum. This is E total. I put it x10 of this minimum position here. That's where this factor of 2 confuses me, so I go through this calculation. Perhaps you find the factor of 2, which I am missing, or if you don't find it, perhaps in the source I used before, it's wrong. So the expression was 2n epsilon for the total energy, A12 sigma x10 power 12 minus A6 sigma x10 power 6. And we can use this term here. Perhaps for this purpose I should rewrite it here. So if we plug in our x10 here, by the way, this factor of n just means that we have, of course, an energy which is proportional to the number of atoms in my crystal. Each atom contributes the same amount. So that's why I always carry this factor of n here with me. So this is A1, A12, A12, and now we have sigma power 12. And we have two A12 over A6 power minus 1/6 power 1/6 minus 12, so this is power minus 2. And here it's 1/6 power 1/6, and since it's in the denominator, it's minus 1.
But if sigmas also should go. X1 is given in terms of sigma.
Yeah, you're right.
So it will have a sigma power 12 and
Yeah.
sigma power 6, which will cancel.
Right. So I have to rewrite them. You see, because here the x10 is proportional to sigma, and this just cancels out here with the other sigmas. And the result becomes pretty simple. That's 1/4. And that's A6 squared over A12 minus, here that's 1/2. And that's A6 and if I'm not completely wrong, 1/4 minus 1/2 is minus 1/4. So I get here minus 1/2 n epsilon A6 square over A12. While in literature source which I used, it was without this factor 1/2. So maybe you go through the calculation or through this paper, I can give the reference. We can check, or maybe I just overlooked this factor in the paper. So, and why is it negative? Of course, I mean, it's a binding energy which should be negative. And this allows now to give real values to our Lennard-Jones parameters. So I repeated these important parameters here. Everything scales what I showed with the nearest neighbor distance R1 or X1, but normally we look at the lattice constant, which is just square root of 2 of the lattice constant. And this minimum position is given by 1.09 times square root of 2. This is this R1 here times sigma. And if we want to have a material like aluminum, which has a lattice parameter of 4.05, we have to put a value for sigma 2.63 roughly. Yeah? So this is, I think, simple. And now the total energy, which is just the cohesive energy of the material. Yeah? How much energy does it cost to, so to say, evaporate all these aluminum atoms, to separate them from each other? Yeah? That's what we call the cohesive energy, which one can look up. And this is, as I said, where I'm a bit confused. In the source which I used, they have this without a factor 1/2, also without a factor with a minus sign is also missing. But basically, this A6 squared over A12 is the same. And the cohesive energy of aluminum is 3 point something electron volts per atom. And this allows to put a value to epsilon of, should be minus 0.2 electron volts roughly. So this is, so far, it's pretty simple. And if you want to study instead copper, I mean, gold has a very similar lattice constant, so it's not so different. Cohesive energy, I don't know, of course. Probably it's much higher because the melting point is higher. Then you can put other values there. Before I come to the other complications down here, I wanted to mention one further point. This is something Guru already mentioned in the introduction of MD. In principle, the Lennard-Jones potential has infinite range. So whenever you do the calculation in MD, you have to sum up over all the neighbors, regardless how far they are away. Yeah? And of course, this would be very time consuming, and the energy contribution of these faraway atoms is not that large. So what we typically do is that we introduce a cutoff. Yeah? Of course, we could say we cut off the potential here after the fourth neighbor. Yeah? And if you sum up, I mean, that's already a pretty large number of atoms. Yeah? We had 12 plus 6 plus 24 plus 12, so it's 54, I think. Yeah? And you see that you still make a considerable error. So the larger the cutoff, the more precise your calculations will be. That's one thing, but it's a compromise between computational efficiency and numerical precision. The other thing is, if you make a sharp cutoff, that you just say beyond this fourth neighbor, I put the potential to 0. You risk, if atoms are slightly moving beyond this cutoff distance, they suddenly don't feel any interaction with this first atom. Yeah? Which can lead to very strange results. That's why we typically do what we call a smooth cutoff. Yeah? So instead of just cutting, we somehow bring it to zero here. And one way is shown here. You just take a sufficiently smooth function, which you put here, perhaps with the same tangent as it is here, and then smoothly bringing it to zero, so arctangent function or so. Yeah? So there are different ways to do this cutoff. And to be honest, I forgot what I used here, or what I put here to plot this function. I could look it up. But that's a typical way. And that's common for all these potentials. But that's more a technical point, but a very important technical point. Yeah? And in our case, in metals, the potentials are sufficiently short range. You have other materials of interest which have much longer ranged interactions, ionic crystals, for example. And there you can't just do a cutoff. Yeah? I mean, electrostatic interaction decays very slowly. Yeah? So there you have to be very careful about the range of potentials. I don't know whether you know Ewald sums. If you have an ionic crystal, you have the positive and negative charges, which to some extent compensate each other. So these are tricks you have to apply there. So that's the first point. Second point is, now this is more relevant for the Lennard-Jones potential, that we have other parameters which we also are interested in. And a very important parameter or very important material properties are elastic properties, elastic constants. And now we have spent all our freedom. Yeah? So we can't attribute values to any parameter to adapt the elastic constants. I will explain in a moment how we obtain the elastic constants. But here you see the expression for the bulk modulus, so the modulus of compression, which comes out for Lennard-Jones as this function here, epsilon over sigma power 3. And as I said, there is no freedom. Yeah? So if I choose these values, I fit it here, the lattice constant, the cohesive energy, I get a bulk modulus which is about a factor of 2 larger than the experimental one. Other quantities which might be interesting, vacancy formation energy. You take out one atom from the crystal and calculate the difference of your initial structure with one atom less, so the energy per atom minus 1, and minus the energy of this crystal with a missing position. Yeah? This gives a vacancy formation energy, which is typically a quantity which is also tried to fit to if you have other types of potentials. Phonon spectra, thermal expansion, and so on. Yeah? So these are all experimental or quantities which should come out correctly. If they don't, you have limitations of the applicability of your potential. And I just wanted to say how we obtain the modulus. Yeah, it's defined as, I use this, the relative change of volume under a given pressure. And what you, some our potential function, our energy function looks like this roughly. And we have our equilibrium lattice constant here. So from one atom, the neighbor is, or the second neighbor is here. And now if you compress your crystal under hydrostatic pressure, you slightly decrease the lattice constant, so you would shift it to the side here. Or if you expand it, you go here. This increases the energy. And an increase in energy corresponds to a restoring force. So if I increase the energy because I compress, there's a restoring force tending to expand it again, and vice versa. And this is what we call the bulk modulus. And what I already plotted here, it's given by the curvature of the potential. Of the total energy. Now I switched from the parameter nearest neighbor distance to the lattice constant, but I think it's not so difficult. So you have curvature is the second derivative. At this point here, and it's given by the inverse of the curvature. So the stronger the curvature here, the narrower the potential, the more difficult it is to deviate from this equilibrium position. Yeah? And the curvature of the Lennard-Jones function here is fixed, yeah? If you fix the parameters. So you have no choice. That's why we have a given value for the bulk modulus here. Yeah? If you want to have a larger modulus, you have to modify probably preferentially the sigma to get a narrower minimum here. Then you increase, or if you would decrease, you blow it up so that the curvature gets weaker. That's basically one of the limitations here. And there's one further limitation which I want to mention, which is, I would say, particularly annoying, and which is very general. I mean, of course, we could construct pair potentials with more parameters. Yeah? I mean, I will show one further, the Morse potential, which, no, I think it also has only 2 parameters. But in principle, you could construct functions with 3, 4, 5 parameters, but still pair potentials. But in general, this, of course, this relaxes some of the problems. For example, this problem about the bulk modulus. If you have a third parameter, you can stretch the curve around the minimum or so. Yeah? This would solve this problem. But there's one principal complication. Where do I have it? So here's this conclusion which I gave, that the Lennard-Jones potential is not very flexible. But this general limitation of pair potentials is more severe. You know that in a crystal we have so many elastic constants depending on the symmetry of the crystal. I think the highest number of elastic constants is 18 or so. And then the higher the symmetry, the lower the number of elastic constants. For a cubic system, you normally have 3 independent elastic constants. Yeah? If we speak of the C constants, it's normally we use C11, C44, and C12. Yeah? If you use a pair potential, you get a further constraint, a further condition for these elastic constants, so-called Cauchy relation. The Cauchy relation says that I use this, not the Vogt notation here, but the 4-index notation, that any permutation of the indices does not change the value of this parameter. Yeah? So for example, C1122 must be equal to C1212. Yeah? C1122 is C12. C1212 is C44. So this means that in a material which we describe with a pair potential, C12, which is more or less a Poisson ratio, is directly proportional to the shear modulus. And then things can become worse for an isotropic material. You know, you have the condition of isotropy, which gives a further constraint. In an isotropic material, you have only 2 elastic constants. Yeah? With this extra condition, you have only 1 remaining constant. And that's not very much, I would say. Yeah? So if you fix the bulk modulus, you have the shear modulus fixed, Young modulus fixed, and so on, which is not very realistic. So that's one drawback of.
So the permutation, Ij can be permuted with Kl, and within Ij and Kl you should be able to switch them.
Yeah, but this does not change.
1122 being 1212 comes from the fact that we have a potential and partial derivatives, if you take in order, does not matter. So we get this C12 as C44, which is specific to this potential. Right? In general, we don't expect C12 to be the same as C44.
No, for sure not.
Right?
Yeah.
So this is to do with the fact that this is a curvature we are taking of the potential,
Right.
and order of partial derivative does
Yeah.
not matter.
Right. Yeah. So that's one drawback of pair potentials in general. So it does not help to make a more complicated pair potential. That's what I wanted to say. Yeah? So we need many body interactions to describe solids realistically. Another drawback is that the cohesive energy increases here with an atomic number and here with a square root, which perhaps is not so clear here. And the vacancy formation energy in pair potentials comes out to be more or less equal to the cohesive energy, but in realistic potentials or in experimental situations, it's more a factor of 1/2 of the cohesive energy. So these are all drawbacks of pair potentials in general, and I think we could make a short break, and then we can continue with the more complicated potentials, which still have their problems, but at least they have more parameters which allow a more realistic description of solids. So we want to do better, or at least for some applications it's advisable to look for better potentials than the Lennard-Jones. And what is required for a good potential? What is a good potential? I mean, there's a huge amount. There's even a database somewhere, I think at NIST or so, where you can download potentials for different purposes. I think it's mostly for metals, but then there are other potentials and so on for molecules and for biological material and so on. So what do we need? I mean, first of all, of course, it should reproduce our material properties as well as possible, which is not so easy as it sounds. But then the typical procedure is what is done if you construct such a potential, that you take experimental or values from DFT and try to fit your potential expression to these experimental values. That's nice, because then you know my potential probably reproduces these values I put in. But that's not all what we expect. We expect that it also has some predictive power, yeah? That we can use it for situations to which we did not fit it. Yeah? So that's the second point here. The third point, what is typically among these people constructing the potentials, is called transferability. That means if you fit your potential to, say, a diluted aluminum copper alloy, that in the best case it also works for an intermetallic of aluminum copper. Probably this will not do it. No? So this is a bit similar to this predictive power. And then on the other side, you always have computational limitations, whatever size your computer has. So it should be also fast and simple, which is, sounds simpler as it is. Because most part of a MD calculation, I think, goes into the potential calculations or force calculations. So these are general requirements. And how can we do this? I already said pair potentials are not in all cases the best choice. Make it kind of Taylor expansion, or not Taylor, kind of expansion here. We have our potential, which depends on so many neighbors, or the interaction depends on so many neighbors. The first is trivial, that's the interaction with itself. But then we have the pair potential contribution. So the interaction of one atom with any other atom was just one by one. And then the next step could be to introduce triple interactions, quadruple interactions, and so on. This is what we call many body terms. And to overcome these limitations of pair potentials, one at least would have to introduce such a triple term. And here is again shown which parameters we can use beyond the lattice constant and the cohesive energy or the depth of the potential. There are more parameters. As I said, the curvature here in the minimum gives you the elastic properties, the bulk modulus or so. But then other terms of interest, for example, are thermal expansion. And I don't know, do you know where thermal expansion comes from? Why do most materials expand if you heat them and do not contract? The typical answer is because of the lattice vibrations. But if you take a purely harmonic crystal, you see it here, the amount of energy you lose if you expand it is the same as if you compress it. Yeah? So there is no thermal expansion. It only comes from the asymmetry here. Yeah? If as is always the case, if the potential is softer here, as it is here, it's easier to expand it than to compress it. It's not for all materials, but for most materials it's like this. And this is what we call anharmonicity. Yeah? Harmonic means that you have a perfect parabola here, which is hardly the case. And if this asymmetry is more pronounced, you get stronger anharmonic effects. And anharmonic effects, as I said, are responsible for thermal expansion. That's one point. But also for thermal scattering and so on, so thermal conduction. Perfect crystal, I think, would not conduct heat by phonons because you don't have phonon mixing or so. Yeah. So that's a further parameter one can use to fit material properties or to fit potentials to material properties. Then this steep part here, this is of course responsible for the resistance against very high pressure. Yeah? Then you press the atoms into a range where this strongly repulsive part comes into play. So here you can, what is called high pressure properties fit to your potential. And then of course there are other a bit more complicated parameters which cannot be seen directly from such a potential curve, like stacking fault energy or vacancy formation energy or defect property, other defect properties. which you can all use to generate such a potential. And one rather common potential, type of potentials for metals are the so-called embedded atom method potentials, EAM potentials. I will briefly motivate what the idea is behind it. These are many-body potentials, but not in the sense I showed before, that you add, besides the pair potential, you add a triple term or so, but you add kind of general term. Why do we do it? It has to do with the nature of metals, of metallic bonding. Metallic bonding is caused by the electrons, by the electron gas, the free electron gas. Yeah? And it's not a pairwise or so interaction, but can be considered just as a delocalization of the electrons and the electron density. The higher the electron density, the stronger the binding or so. Yeah? And now what we do is we consider our crystal with some pair bonds. This is the standard way, so we have a pair potential. And then we add something to this pair interaction, which is called the embedding energy or so. Yeah? So we have this overall delocalized electrons, which are responsible for all the properties, not all, but many properties a metal has. Yeah? For example, electrical conductivity is caused by the free electron gas. Also, and I think, I'm not sure whether we come to this, thermal conductivity in metals is mainly based or mainly caused by the electrons. Yeah? Thermal conductivity, normally we think of, thermal energy is lattice vibrations. So the propagation of lattice vibrations, one naively assumes, is caused by propagation of these vibrations. Yeah? But one can calculate that I think roughly 90% is not coming from the lattice vibrations, but from the electron gas. Very roughly speaking, the energy transport is something like the momentum times the density. And the phonons have very low momentum, the lattice vibrations. So the transfer of energy is weak. The density is high, but the electrons, they have high momentum. They have more or less a Fermi energy or Fermi momentum. Yeah? And still you have sufficient number. So very roughly speaking, and if you go through the calculation, you get the result. And that's one of the weaknesses or one of the problems you often have in MD simulations. You completely, except for the potentials, you completely leave out the electronic properties of the material. Yeah? So if you study some high energy phenomena, for example, there was a lot of irradiation effect studies using molecular dynamics. Yeah? You shoot a fast particle on a crystal and then you study what happens to the atoms which are hit by this fast atom. Yeah? Something which happens in a nuclear reactor, for example. So irradiation damage or so. Yeah? But the problem is this incoming fast ion or whatever it is brings a lot of energy with it. Yeah? And you have to transport away this energy. So if a kilo electron volt or even more energy carrying ion flies in, you have to get rid of it. And heat conductivity in molecular dynamics is only via phonons, via lattice vibrations. You have no electrons basically. Yeah? So you have to construct some very artificial models to carry away the energy. But that's a side remark, yeah? Just to make you aware that there are further complications. Okay, but somehow we try to take into account the electron system. That's why we use this electron gas, which is cartooned here. So what we do is, besides the pair interactions, we try to construct a kind of delocalized electron gas by a contribution coming from each atom here. And then we have what is called an embedding function. So if I take another type of atom here on one position, it brings another density of electrons with it. And the density of the electrons, this here, is characteristic for this type of atom. And then how much it contributes to the total energy is given by what we call the embedding function. So if we have a particular density of electrons somewhere here, we obtain such an embedding energy. So that's the idea of this EAM method. There are kind of derivations of this method. There's a special type of these EAM potentials called Finis-Sinclair potentials, where they claim that it is based on some real electron theory considerations, but don't take it too serious. Yeah. I mean, I would just take it as a clever way to construct such a potential. So what we need.
So it has basically two interactions. One is interactions energy, another is the embedded energy. Embedded energy is the functions of the electron gas means.
I come more in detail how to really set it up. Yeah. So if you have an alloy, yeah, or maybe we start with a pure metal, then you have just a pair interaction and this embedding of all the atoms. These two contributions here. The interesting part is when we have an alloy. Yeah? Then still you have the pair interaction with, say, copper and zinc. No, copper and copper, zinc, and copper and zinc. So we need three pair interaction functions here, which also depend, of course, on distance. And then we have this density contribution coming from a copper atom and coming from a zinc atom in this distance here to the starting atom. And then we have to plug in this calculated density into this embedding function. So we have a pretty large number of functions, each with a certain number of parameters, and that's one of the reasons why these EAM potentials work rather well, I would say. Yeah. But to say it already here, there's no directional dependence. Huh? All depends only on distance. That's one of the problems also. Yeah, so. IJ or then we have this electron density, which is contributed by an atom of type I. In a distance somewhat away from the atom of interest. Now I have to switch my, yeah. So I should write it this way. At position I have the surrounding atoms which contribute to the electron density, some function and this also depends on the type of atom. And then we have this embedding function. So the embedding energy translates the density of the electrons at this position of atom I to an energy. So I have a certain density at my atom interacting with the neighbors. So the total energy then as before is obtained that I sum up all these individual contributions. These are the pair contributions as before, now plus the sum of all these embedding energies summed over all I. This would be for a pure metal. And for an alloy, you now have to distinguish all these functions here. This phi depends then on the type of atoms you join here. These density functions then also depend on the type of neighboring atom. So, and the embedding function also, of course, will depend on the type of atom on which I consider or I determine the energy. So the situation we have in mind is we have an atom here at position I of type X, and we have surrounding atoms J of type X or Y. And we sum up all these contributions. So for a binary alloy, we have 3 pair potentials. Since we have 2 types of atoms. We have two electron density functions. So it's phi AA, phi AB, phi BB. Here for the electron density we have rho A and rho B, or FA. And for the embedding function again, two embedding functions I wanted to write. FB. The question is how to construct or how to obtain them. And the answer is, like in the case of Lennard-Jones, we make some, or one possibility at least is we make a functional parameterization. So what is often chosen is something similar to the Lennard-Jones function for the pair potentials. For example, the Morse potential. So this phi xy could have the form prefactor, which controls the depth of this 1 minus that's a common choice for this pair potential function. You have parameters dxy giving the depth and this alpha giving the range. This is just the position of the atom. No, position of the minimum. So here you see a graph of this Morse function compared to the Lennard-Jones function. You see they are pretty similar. Perhaps the range is a bit shorter and the increase is a bit steeper. And you have here the curvature, which you can still adjust. So what I used here was depth equal 1 or minus 1. This minimum here at 1.12 to fit with the Lennard-Jones function. And then you have this parameter alpha. I just used 5. This is a further freedom you have that you can adjust the curvature and the minimum using this factor of alpha. Then for the electron density, in principle one could do quantum mechanics and try to determine these electron density functions, but there's a very simple parameterization that one takes one particular of the hydrogen orbitals. I'm not sure whether you're familiar with these terms. Hydrogen has the different quantum numbers, SPD, the angular momentum quantum number, and then the major quantum number, principal quantum number 1, 2, 3, 4, and so on. And people like to use the 4s. Often. I think the reason is mostly, it's an S function because it's angular symmetric or spherically symmetric. If you would take an angular dependent P or D, this would introduce other complications. And then it's sufficiently simple, you know, an analytical expression for it. A strange prefactor here, 2 power 9, 512. I forgot where it comes from. It's monotonically decreasing, so I can show it. No, of course it's not monotonically decreasing. The probability of the electron to approach the nucleus becomes 0 here, but we take the part which is monotonically decreasing. We only want to have the electron density which is contributed to the electron gas. So we use this branch here of this 4s function here, and it's spherically symmetric. So this is just one parameterization. And then, in principle, we would need also the embedding function, but at least in some cases one can avoid. This f of rho. One can choose it in a way that what is called the universal equation of state is fulfilled. What is meant by this? There are more or less empirically found laws which tell you how much the energy changes if I vary the lattice parameter. So that's minus the decrease of energy, 1 plus this parameter A star. A star is a scaled lattice parameter, exponential minus A star. This is A star. This contains the bulk modulus and the atomic volume. So what are these quantities? So this is a scaled lattice parameter. B is the bulk modulus. Omega the atomic volume. EC, the cohesive energy. And A0, the equilibrium lattice constant. So there are different types of these. This is, I think it's the Birch-Monaghan. Or is it Rose-Vinay? I don't know. So this tells you how much the energy changes if I vary the lattice constant. And yeah, we, or a student of mine, he went through these calculations with these functions which I just gave, the pair interaction function, the embedding function, and then this Monaghan state of equation of state. His PhD, it's 10 years ago, no, it's longer than 10 years ago, 14 years ago. He fitted the parameters which are given here to a system tungsten thorium. Why were we interested in such a strange alloy at this time? He worked for a company, Osram. Perhaps you know Osram. They produce these lamps and so on. And they also produce welding electrodes. And welding electrodes, for arc welding, they contain a certain amount of thorium. And it's not really understood what it does. I mean, due to its radioactivity, apparently it helps to ignite the arc. Yeah? So they have to have this small amount of thorium in it. But they don't know how it is distributed, how it segregates to grain boundaries, how it segregates to dislocations and so on. And that's what this thesis was about. In the first step, I mean, that's such an exotic system. The first step was to construct such a EIM potential. And here are the parameters which he used for the fitting. That's a lattice constant. Some of the parameters are not easily obtained or not available or so. He did a lot of ab initio calculations also, if experimental parameters were not sufficiently safe or so. I mean, the lattice constant should be safe, but other parameters. So you see here these parameters which he used. The equilibrium lattice constant, the cohesive energy, the bulk modulus, and some elastic constant, vacancy formation energy. This I even forgot what it is, this parameter. And then, this is the first part for the pure metals, and then you need parameters for the alloy. I mean, for the pure metal, you have the pair interaction between tungsten and tungsten, thorium and thorium, and then so on. But then you have also to have the mixed systems, the mixed parameters, in particular the pair interaction between tungsten and thorium. Yeah? For this, it was even much harder to obtain experimental values. In fact, there are no or very scarce. So again, he did ab initio calculations. And what he did was to construct fictitious intermetallic phases. Simple enough to parameterize them. So he used a B2 phase, an L12 phase, and I think also others. And from these he obtained equilibrium lattice constant, bulk modulus, and so on. And to these parameters then he could fit these mixed pair potentials. Often, I mean, there is no mixed electron density. You have the electron density from one and the other, but you have no mixed term there. So you need the mixed pair potentials essentially. There's one strange point. You see here that here is a negative, what is it, sigma 1, 1? I think it's, which means that this structure is not stable. It collapses. But this does not matter even in the ab initio. This structure is also not stable. And here you see a plot of these functions. What is this? This is a thorium-thorium pair interaction. That's the mixed pair interaction, and this is the tungsten-tungsten pair interaction term. So they look similar to what I showed before. He used this Morse potential and the embedding functions here. And this results then in a set of constants. Here's this embedding function which he derived from this equation of state. Had a list of the parameters he used here. Forgot to copy this long list of parameters, but essentially it's not of interest. So this is how one can proceed, and then one can do calculations. I will later on in other parts show results also from his thesis about phonon spectra and so on. So all the things he derived from these, using this potential. And of course, nowadays, at least for standard alloys, there are often potentials available. But nevertheless, one should always, if you use such a literature potential, check whether it really gives the values or reflects the situations you are interested in. Often you have to make a compromise. For example, some potentials chronically are bad for stacking fault energies. And you know that stacking fault energies are important for dislocation splitting. So this can lead to situations where the dislocation splitting is far too small or far too large or so. And one slight enhancement of the EAM potentials are the so-called MEAM potentials. Fit experimental or ab initio data, DFT data, determine the necessary parameters. And then best is to check for other parameters, other quantities which were not fitted, whether your fitted potential gives reasonable values. For example, you omit the lattice distortion caused by a copper atom, and you try to determine it from your potential. Yeah? And the next step would be to go to MEAM potentials. At least it's one step one can take. The M stands for modified. one of the drawbacks of the EAM potentials is that they are not angular dependent. They are only depending on the distance of the atoms to each other. You introduce the many-body interactions just via this electron gas, which is also non-directional. And in many situations you have certain directional dependencies, so that's why they develop these MEAM potentials. And they do it via the electron density, I think mostly because it's the easiest way to do it. One might argue that this is kind of replacing the 4S function which we used before by some P or D function, but this is not precisely what is done. So what is chosen here is that you have your density as before coming from the neighboring atoms, plus now summation over 3 atoms ik of sorry, this sub ik is useless here. Times the cosine theta I j k. So you have your atom I here, you have atom J here, and you have a third atom K here. And in a simple EAM, it's just the electron density from this atom here. Okay, this computer is cleverer than me. And now this is the standard EAM, where you have the electron density from atom J reaching atom I. And now you have a term which depends now on this angle here, theta. Which gives a further contribution, perhaps something like this. What? Oh, okay. Was not well plugged in. Okay, I think I don't go more in detail into the MEAM potentials. I have a last chapter on the potentials. Perhaps we can finish that after lunch, which is on neural network potentials. That's the last development. It's a short chapter, but it's very fancy at the moment. Everybody wants to use artificial intelligence if the natural intelligence is not sufficient or so. So it's a kind of hype, but I want to explain, and I mean they are powerful, no doubt. Yeah. So I will explain roughly what people are doing there. But before, I think we go to lunch.